With the puzzles that we're going to be doing today, trigonometric identities, basically you're going to be substituting things or values in that are equal to each other to try to reduce or simplify different equations. And like I said, this packet is going to take us 3 lessons to go through. So today is just basically 5.1. 5.2 will be next time, and 5.3 will be the time after that, but it's all in one because it all goes together. Now, trig identities express important fundamental relationships amongst the values of different trigonometric functions. These identities are useful whenever expressions involving trig functions needed to be simplified. This is a skill of extreme importance for the study of calculus. So if you're taking calculus next year or taking calculus in college, this is going to be like a very basic step in larger calculus problems. But identities are somewhat familiar to us. You should know all of these reciprocal identities. Do those look familiar to you? We've used the reciprocal identities to know that they're reciprocals of each other, but now we're going to use these equation versions of the reciprocal identities to try to simplify different trig functions. For later, pretty much not today, but reciprocal identities, to write down those words, that's a lot of letters. So I'm going to shorten that to RECID. So if ever I'm writing down what I'm doing and I write RECID, I'm talking about a reciprocal identity. It's just way too long to write all of it. Quotient identities are also familiar to us, right? That tangent is sine over cosine, which means cotangent is the reciprocal of that since they're reciprocals. Those are called quotient identities because they create fractions between the trig functions themselves. The shorthand for that I'm going to use is called QUOTID, quotient identity. Just too many letters if you write all of that out. But after that, the rest of this is pretty much going to be new for you. Pythagorean identities are another set of equivalencies between different trig functions. So if we zoom in for a second on these Pythagorean identities, we have the first one that sine squared theta plus cosine squared theta is equal to 1. That means if we're ever trying to simplify a trig function and we see this, sine squared theta plus cosine squared theta, you could basically mark it out and put a 1 because they are equal to each other, so we can use them equally. Now notice here, when you have sine squared, you probably noticed this in the blue kit, the squared does not go behind theta, it goes behind the sine part of it. That's how you indicate sine as being squared instead of theta being squared. But what's nice about these identities is because they're equations, we can solve them for different things. Right now, it's set equal to 1. But if I wanted it to be set equal to cosine squared of theta, what would I have to do to get cosine squared theta by itself? Subtract sine squared theta, right? So we have an equally, you would write this down. We have an equal Pythagorean identity that cosine squared of theta is equal to 1 minus sine squared of theta. If we notice that, 1 minus sine squared theta, we know that that is equal to cosine squared theta. And we can substitute it in, make it simpler. Let's say, however, we didn't want this. We wanted it to be solved for sine squared of theta. What would I do to get sine squared of theta by itself? Subtract cosine. So sine squared of theta would be equal to 1 minus cosine squared of theta. So again, if we recognize 1 minus cosine squared theta somewhere in my equation, I can just substitute it for sine squared theta. That's our first of 3 Pythagorean identities. The second one is a relationship between secant and tangent, which feels like an odd pair to me, but it is the non-co versions of the things left over after sine and cosine. What I mean by that is if you look at the next one, that's cosecant and cotangent, so the co's go together. That's how I've kind of remembered it. But this identity says that secant squared theta minus tangent squared theta is equal to 1. So if we recognize that, we know we can substitute in a 1. Let's say, though, I wanted this to be solved for secant squared theta. How would I solve this for secant squared theta? Add tangent to both sides. So secant squared of theta would be equal to 1 plus tangent squared of theta. So there's another identity we got just by solving that equation for something else. We can still substitute in secant squared theta if I see 1 plus tangent squared theta. Okay, but what if I wanted it to be solved for tangent squared of theta? And I'm looking specifically at this one because it's one of the intermediate steps to solve. If I wanted it to just say tangent squared of theta equal, what would I have to subtract? 1. So an equivalent version of this is tangent squared theta equal to secant squared theta minus 1. So here we have the second identity solved for all three versions of its formula. Derived for 1, derived for secant squared theta, and derived for tangent squared theta. The third and final Pythagorean identity is the cosecant squared theta minus cotangent squared theta is equal to 1. So if we rewrote it to where it was solved or derived for each of the other ones, this would be cosecant squared theta equal to 1 plus cotangent squared theta. Or cotangent squared theta equal to cosecant squared theta minus 1. So all of these things are going to be things we're going to try to recognize quickly so that we are able to simplify more complicated looking trig functions or trig expressions. Okay, the next two are sub-identities. Oh, I didn't tell you the shorthand for Pythagorean identities because, again, that's a lot of letters. When I'm talking about it, especially in a proof that we'll get to next time, it'll just be shorthand Pythagorean identities. The next two little boxes are identities that we've kind of discussed before, but not really in this way. The cofunction identities are the relationship between sine and cosine, how they're just translations of each other horizontally, and same for the other functions. We just maybe didn't write it this way. But basically, they're all 90 degrees shifts of each other. Sine and cosine are 90 degree shifts of each other. Tangent, cotangent, 90 degree shifts of each other. Secant, cosecant, 90 degree shifts of each other. That's all that's really talking about. Your even odd identities are coming from this. So we've seen these identities in use due to all-star trig class, but I don't know if we've ever written them out like this. So when you have positive and negative angles, you either have a positive or negative trig function, trig value. And that really comes from all-star trig class. So we're not going to spend a ton of time on that because it's not as important. The last one down here, sum and difference formulas, is very important, but not until the third part of these notes. So it's on the front so that you have a formula chart essentially on the front of your notes. We're not going to use it today at all. Just so you have the shorthand up here, we're going to call that sum and diff IDs. But we're not discussing those today. We will discuss those later. But now that you just have it.
Which ones are we learning today?
We are basically only going to be working with the top three. So the first two of the top three we already know because the reciprocal identities, quotient identities we're familiar with. So Pythagorean identities is truly the only new thing. But we've never used them in the way we're going to use them today. Okay? So what you do with these identities is like the problem on the back. We have number one that says sine of theta, cotangent of theta. And we want to simplify them using identities into a single trig function or a single number. So we're trying to simplify here. The only things you can use are going to be the reciprocal identities, the quotient identities, or the Pythagorean identities. And like maybe factoring and multiplying. Okay? So we want to start trying to create ways that things cancel or change into different trig functions so that I end up with only one trig function at the end. Here's what I notice first of all. Don't we have a quotient identity for cotangent of theta? Right? That's on the front page. What is the identity for cotangent of theta if we look at the quotient identity? Cosine of theta over sine of theta. So I didn't do anything to this function. All I did was rewrite cotangent as cosine of theta, sine of theta. Those are equal to each other because that's one of the definitions of cotangent. Correct? So we've used the quotient identity. What do you notice is going to happen here? Things are going to cancel. The signs are going to cancel each other out because one is in the numerator and one is in the denominator. So what do I have left? one trig function, and I'm done. We're trying to simplify these things down so that there is only one trig function remaining. The thing is, you have to get creative in how you're doing that. With these problems, your work is your answer. So if you're just putting in the final things for me, that's not it. Your work is how you get there. The work is what I'm grading on these kinds of problems. If we look at number 2, we have sine squared of theta, sine squared theta over cosine of theta times cosecant of theta. We're only going to do one thing at a time. The first thing I'm going to do, just because I don't like working with the reciprocal functions, I want things to be in sine and cosine pretty much at all times. That's just my preference. Is I'm going to change that cosecant of theta into its reciprocal. What is the reciprocal of cosecant of theta? 1 over sine of theta. Okay, cool. So I have the first part, which I didn't touch, and then the second part, which I've changed to 1 over sine of theta. I've done nothing to this problem other than rewrite cosecant of theta with its reciprocal identity. What do you notice is going to happen? It's going to cancel out. There are 2 signs multiplied together in the numerator and then the sign in the denominator. So it basically gets rid of one of the 2 that are squared. So the thing that I have left is sine of theta, because it was squared and now it's just regular, and cosine of theta. My answer should be one trig function. What is sine of theta over cosine of theta? Tangent. What is the identity called that let me do that?
Quotient identity.
The quotient identity. So tangent's quotient identity is sine over cosine, so I could rewrite any sine over cosine as tangent. Done. It's one trig function. I've gotten the correct answer. Okay, pause before we keep going. In these first 2 problems, what are your questions? All right, so number 3. When we look at number 3, there are a few things we could do. One of my first instincts was, okay, we have something in front of a set of parentheses, which means we could distribute it into the parentheses. But when I distribute it into the parentheses, does it simplify anything at all, or does it make it more complicated? So we could maybe do that, but let's try to find a more simple way to do it. Here's what I want you to recognize. Do you see this anywhere on your formula charts? It's sine squared of theta. Which identity is that called? The Pythagorean identity. 1 minus cosine squared of x is the same thing as sine squared of x, or theta. So we've got cosecant squared of x times sine squared of x. What should we do next? Because remember, we're still trying to get things to just be one trig function.
Cancel the squared.
Can't do that.
We make cosecant 1 divided by sine of theta.
Absolutely. There's a reciprocal identity for cosecant squared so that we can rewrite this as 1 over sine squared of x multiplied by that sine squared of x that we have already. Notice the square follows because it's the reciprocal. What do you notice could happen now?
Cancel.
They cancel out, so guess what the answer here is? 1. Now remember, the answer is whatever. Cool. That's how you know you're done. But the work is the answer. Seeing each step happening one step at a time is how I want you to do these problems.
Well, what if you can do it in your head?
You're not doing it in your head. You're showing me on the paper. It will be wrong if you do it in your head. I'm telling you that right now. Your work is your answer. Yes?
What if I don't understand my own work?
Then I need you to make it make sense.
Make
Okay.
Make it into degrees.
Okay, for number 4, again we have something inside or outside of a set of parentheses. This time, if we distribute it, does it make at least one of them more complicated, or does it kind of simplify it down? Kind of simplifies it down, because sine times sine, isn't that sine squared? So what we're going to do is we are going to do this distribution and see what happens. Now, sometimes with these problems, you'll try things like distributing and it'll get more complicated and not reduce down. You're like, that's when you get a good eraser. You're like, oh, never mind. This is a homework I would do in pencil. So this one would be sine of x times cosecant of x minus sine squared of x. So far, all we've done is distribute. Yes? Okay, what could we do next? Like I said, I like putting things in sines and cosines. So what could we do with this to get it to be a sine or a cosine? Reciprocal identity. What is the reciprocal of cosecant? Sine. Oh, snap, look what's going to happen. If you have sine of x times 1 over sine of x, those are going to cancel. So you have 1 minus sine squared of x.
Oh, yeah.
And it should just be one term. What is...
Cosine squared.
Yes, cosine squared of x. So this is the Pythagorean identity again. 1 minus sine squared of x is cosine squared of x. And once it's a single trig term or a single number, like we got 1 a second ago, you're done. But your work is your answer.
Wait, where did you get 1 minus sine over?
Sine over sine cancel each other out. And so like when 5 over 5 cancels, it's 1. So sine over sine cancels, it's 1. Yeah. Okay. Cool. See how they're just kind of like puzzles? I think they're really fun. Okay. Cool. Well, you're going to do one thing at a time. I see that it has cotangent squared of theta. On your formula chart, is there something that uses cotangent squared of theta?
Yeah.
Cosecant minus 1.
Yeah, the Pythagorean identity, right? So we would need it to say cotangent squared of theta plus something to be able to change it, right? It's cotangent squared theta plus 1. What would that be equal to?
Cosecant.
Cosecant squared of theta. So we kind of have a goal in mind, since we have that cotangent squared, that we need the second thing to turn into 1 so that we can use the Pythagorean identity. Is there a way you can change something in the second term here so that this becomes a 1?
You do 1 over sine
Oh yeah,
sine,
inverse of
and then you get 1.
Yeah, so cosecant, remember, is the reciprocal of sine, so we can use the reciprocal identity to change cosecant into 1 over sine of theta. And sine of theta times 1 over sine of theta, the signs cancel. This would be cotangent squared of theta plus 1. Now that we have cotangent squared of theta plus 1, we use the Pythagorean identity to change that to what? Cosecant squared of theta. And since it's one trig function, we're done.
Oh my god.
Maybe we have to memorize these.
The one printed on your paper, yes. All of the derivations of it, no, because you can solve for the derivations. So I just want the one printed on the page to be memorized. I mean, it'd be great if it was the other ones too, but for sure those. Okay. Number 6. What kind of problem is number 6 when you first look at it? Oh, it's almost Pythagorean identities, but we need squares for them to be that. What bluekit did y'all do when you walked in today?
Square.
Isn't this the factored version, difference of two squares?
Yes.
So if we were to use the difference of two squares to change this back or to multiply it using that special property, this would just be sine squared of theta minus 1. That's why knowing those special properties cuts you out a lot of work here. Okay, do you see sine squared of theta minus 1 anywhere on your sheet?
Cosine.
Ooh, look again. Is it sine squared theta minus 1? It's 1 minus sine squared of theta, right?
Also,
What
it's
is the
called
difference?
secant.
No. So you're looking at cosine squared of theta equal to 1 minus sine squared of theta, right? That's what's on your formula chart.
Yeah.
That's a different order, and subtraction order matters. So those are not technically the same right now, unless we somehow get the signs to change to where the 1 is positive and the sign is negative. What could I do to this problem to get the 1 to be positive and the sign to be negative? There's no other side. It's a good idea. There's no other side though.
Multiply it times negative.
Multiply it by times -1. So if we took this whole thing and multiplied it by -1, it will change the signs of everything inside of it. I'm just going to rewrite it where they're in the opposite order because then it looks like the thing on my formula chart. But truly, that changed the signs, right? 1 became positive and sign became negative.
So now it's
So now it fits my Pythagorean identity. Now this can be changed to what? Negative cosine squared of theta. That's a single trig function. I'm done. So if you have the right terms, but they're the wrong signs, or they're like flip-flop backwards with subtraction, addition can be in whatever order, obviously, but subtraction has to be in the right order. Just make the whole thing negative. Yes? Okay. All right, number 7. Take a look at it for a second.
I'm looking.
What do you notice?
a cube.
There's a cube, okay.
Oh, there's a cube.
There's 3 different x's. What is it?
I have a question.
Yeah.
Can we just essentially, if you were to add, sign, if you were to add the two signs, you would get, sign to the fourth, right?
Multiplying changes powers. You can only add terms that are like, even when it comes to trig functions. So these are not like terms, so we can't combine them.
Oh god.
Here's what I notice. So again, I'm trying to alert you to things that you'll need to look for and maybe when you're doing these problems. You've got a sign here, and you've got a sign there, which means there is a like term, or a common denominator, I guess I should say, between the two, a common factor. If we factor out the GCF, what they have in common, we are taking a sign in the very front of a set of parentheses. What's left over if I take out one of those signs? Well, the first term just becomes sine squared of x because it lost one of its signs. And what is the second term? Cosine squared of x. Did I make that more complicated, or did I find a way to make this less complicated?
Wait, I was daydreaming.
I factored out, thank you for your honesty. I factored out sine of x. So the cubed became squared, and the sine of x in the second term just goes to the front. So reverse distribution.
Oh, so you gave it to that.
Do y'all recognize this?
Yes.
What is that?
1.
It equals 1. That's the Pythagorean identity. This is sine of x times 1. And what is sine of x times 1? Boom. Done. So there's things you can look for. The problem before this, when we did a difference of two squares, that was multiplying. This time we had a factor. All of this algebra stuff that we've been working on for a long time, you've been taking algebra for what feels like your whole life, comes into play with trig identities as well. So let's see if we kind of we're going to combine some ideas from problems 6 and 7 on number 8. Let's see what you guys think. You and with yourself or with the people next to you, see if you can get this to one single trig function. Okay, so we've gotten this far, right? We took out the GCF of sine of x. We noticed that the stuff in the parentheses was almost the Pythagorean identity. It was just the wrong order. So we multiply by -1 to switch the order. What that means now is we have the Pythagorean identity here in the center. What is that equal to?
Sine squared of theta.
Sine squared of theta. Oh, in this case we're using x, so sine squared of x.
Oh.
So don't overthink this. What is sine of x times sine squared of x? Maybe overthink it a little bit.
Oh.
Always science cube.
Okay, let me phrase it this way. What if you had x times x squared? What is that? So what is sine times sine squared?
Sine cubed.
Sine cubed. That's it. One trig function. Yeah, so they're using the variable x instead of theta. At some point in these notes, I think it's next time, we're using the variable t. It's just a variable. Yes.
Is there ever going to be more than one way to solve it?
Yes.
Oh.
And as long as your way is correct, you will get credit for it. Some of them have one way to make it work. Some of them have multiple ways. On numbers 9 and 10, which is the last thing we're doing today, we're going to leave the rest of the packet for the next couple classes, is these two examples. Oh, look, here's the one where the variable is t. So it's just, instead of theta, we're using t. Instead of x, we're using t. That's just the thing. Okay, no, it's just sine of t, cotangent of t, cosine of t, okay? So, all right, we want to reduce this, simplify it down to one trig function.
Since cost.
No, don't, yuck. Okay, here's what I want to do first, because I see I have sines and cosines, but then I have this cotangent here. I want to get it in terms of sine and cosine as well, because I like things to all be sine and cosine when we're using them. So if I use the quotient identity here, what is the quotient identity for cotangent? Cosine of t over sine of t. All of that times cosine of t. Okay, sure. I don't really see anything to do, so let's just simplify these two. Since they're multiplied together, if I were to multiply cosine times cosine, what would it be? Cosine squared.
What if you just cancel it out though? Or
Well, one is on top and the other is on top. Can't cancel unless one's on top, one's on bottom.
oh, okay.
That's a good point.
What? Can y'all stop talking about smash?
So here's an interesting thing that maybe we forgot about. If we wanted to add, let's see if I can make up a good example here. If we wanted to add 3 plus 1/2 using fraction rules, I know that's 3.5. But if we wanted it to be a fraction, what would I have to do with the number 3 to put a 1 underneath? Can I add them right now?
No.
What else would I have to do?
Multiply by 2.
Multiply by 2, so it has what? What is that called when a common denominator? And when there's a common denominator, I can basically just do this with one denominator and both things on top. So that would just be 7 over 2, correct? Does that check out with our, okay. We need to do that, but with these trig functions. So right now, the denominator of this sine of t is 1. What should it be so they have a common denominator? And if I make it sine of t, what do I have to multiply the top by? Sine of t. So it's actually sine squared of t. Okay. So now, they have a common denominator. And if they have a common denominator, I can write them with just one denominator. Do we notice something? What's 1? The top. What identity allows us to change this to 1? The Pythagorean identity. Sine squared theta plus cosine squared of theta, or t, is equal to 1. And 1 over sine of t is cosecant of t. Look at that.
Oh, well, in a straight line? Hold on, with me. Oh my gosh.
Okay, let's look at that one again, because that one was a little bit different than normal. We had to work on combining like terms, or not combining, finding a common denominator. Did I lose anybody on those steps? Which part?
First part, how'd you put it on
Making this?
the?
So look at your formula chart at the quotient identity. Cotangent is defined as cosine over sine. So I just changed the cotangent to cosine over sine.
But. Oh, yeah, okay.
Okay, last one. There's kind of a big hint up here on the top. What does it look like it's wanting you to do up there? When you multiply them, difference of 2 squares. Now, yes, if you're not comfortable with the special pattern, you definitely can actually multiply it out, but it's ugly. Recognize the pattern. This top, the numerator, would be secant squared of x minus 1 over sine squared of x. Okay, cool. What should we do next?
I don't know.
Secant squared. The hint is that you have something squared We should always look at the Pythagorean identities to see if we can use it.
Squared theta.
What is this equal to?
Tangent squared.
Tangent squared of theta. All right, so we have that is tangent squared of theta, or x, over sine squared of x. Okay. Interesting. Here's what we're going to do. We're going to kind of separate these into two parts. If I have tangent squared of x on top, it's the same as having sine squared of x on bottom. Does that make sense? I've just kind of separated this fraction out where I had the numerator over 1, essentially, and the denominator under 1. Okay?
Wait, do I need to still write 12?
A little bit, yeah.
Oops.
Is there a rule we can use here? An identity.
What is that one called?
The quotient, tangent can change by its quotient identity, correct? What is the quotient identity for tangent?
Sine over cosine.
Okay, cool. So we actually would have sine squared of x over cosine squared of x multiplied by 1 over sine squared of x. Because all I did was change tangent by its quotient rule. I didn't touch the 1 over sine squared of x.
So it doesn't matter if it has a square or not. It can still be.
It can still be that identity, yes. That goes into exponent rules, which we won't describe why, but yes, you can do that. What do you notice?
The signs cancel out.
Signs cancel each other out.
You can see.
So you'd have, when you just rewrite this, 1 over cosine squared of x, which using the reciprocal identity means that it is what? Secant squared of x.
My brain.
They're just puzzles. It's so fun. It is fun.
I'd rather do a 10,000 piece jigsaw puzzle.
I would not rather do a jigsaw puzzle, that's for sure.
You don't have it all the time?